Hello. Um, so welcome back. We're getting close to the end here. Um, Today, I'm going to start discussing magnetic fields. Magnetic fields are the second half of electromagnetism, and thankfully, much of the technology, the math, the integrals, the way we think about the problems with electric fields has been kind of I guess the way I've tried to present things is so that the stuff we were doing before, it kind of flows into what we need to understand magnetic fields. So today I want to introduce the concept of a magnetic field. I want to talk about the force magnetic fields exert on charged particles and maybe do a simple example. Okay, and then in later videos, we'll kind of enlarge on this, or kind of enlarge this this idea, and then eventually work up to how to create magnetic fields. Right now, we're just going to assume that they exist. I assume everyone's seen a refrigerator magnet and maybe the iron filings kind of experiments. So I'm going to assume that everyone kind of knows that story, and you can look at YouTube videos, see how that would go. So I'm just going to assert that there are such things as magnetic fields, and just like electric fields, we can describe them with magnetic field lines, and a lot of the same concepts carry over. Okay. All right. So let me get my notes kind of over here so so I don't get lost. Very good. All right. So what we're going to do is define a magnetic field. The symbol that we use for a magnetic field, you might think it should be the letter M. The problem is that M gets used so much in physics. We don't do that. We're going to use the letter B. It's a vector field. It's very much like an electric field. Okay, it's a vector quantity. It kind of fills space and time in much the same way. All right, so this is the magnetic field. Right, and well, okay, so we had an electric field. How do we figure out the units on an electric field? Well, the way we did it was we went back to the forces, the force law, and that allowed us to relate the electric field to newtons and things. Well, we're going to do the same thing here. So it turns out that I'm just going to claim this without proof, and then we'll work out what its implications are. That the magnetic force on a charged particle. So I'm going to imagine I have, let me draw a picture before I start writing the formulas down. So the idea is going to be, I have a particle, a point particle. So where this is a force on a test charge or on a point particle. I have a charge Q, and it's following a path. Okay. And so, at each point, it would have some velocity vector. All right. And then, let me change colors here. We're imagining that this particle is moving, and there is some magnetic field, and it'll have magnetic field lines like an electric field would. Oh, that marker's no good. Okay, so my magnetic field will be in black. So I have a particle moving with a velocity v, which is tangent to the path, and there's a magnetic field, which is in black. The formula for the magnetic force law on a point charge forces or vectors is equal to the charge, positive or negative, times, and this is where it's weird, the velocity of the particle cross the ambient magnetic field. Now, I haven't talked about how to create magnetic fields yet, but it works the same way. This particle is the one which feels the magnetic force, therefore it's the observer. And the magnetic field will come from other particles, let's say. It's going to turn out that moving particles create magnetic fields. But for right now, we're just imagining that other phenomena in the universe are the sources for this. So the magnetic field is going to be created by the source, whatever that is. I haven't described that yet. And the velocity field, or so the velocity is a property of the observer, and the charge is the charge of the point charge, so the charge of the observer. Okay, we're going to have the same mental split between the source of the effect and the object which experiences the effects, sources and observers. And the force is always on the observer. It's a force by the source on the observer. Okay? Whoa, that's a wacky force law. So let's review everything we know about cross products, or the important things that we need to know about cross products. Okay. Okay. Remember, cross products. Most of you are just coming out of Calc 3, or many of you in statics and now dynamics. And so you guys have been doing this stuff. But if you haven't, or even if you have, maybe it's a good review, cross products. Remember, the cross product takes two vectors and it produces another vector, C. The vector C, the output, is perpendicular to both A and B. Okay, so it's perpendicular. And it follows the right-hand rule. So I'm going to do this in two ways. I'm going to say kind of the first definition I'll give is the magnitude of A cross B equals the magnitude of A, magnitude of B. Here, let me draw a picture here. There's A and there's B. And the angle between them is theta. And when I say the angle between them, I mean the angle less than 180 degrees. If I use the other angle, then sine will start to be negative. So, and it's supposed to be a magnitude. So I need to use the smaller angle to get this to work out. Okay, that's the formula for the magnitude of the cross product, and the direction follows the right-hand rule. What is the right-hand rule? Step 1, take out your left hand. Sit on it. Step 2, use your right hand. And what you do is you start with your right hand, you align the kind of the butt of your palm there, the bottom of your palm, you align it with the first vector, so in this case it'd be A, and then you curl your fingers towards the other one. So in this case, in this example, the right-hand rule would produce a vector which goes into the board. Okay, the right-hand rule. If I do B cross A, so in the opposite order, B cross A, I get a vector out of the board. So reversing the order that you take a cross product gives you a minus sign, changes the answer. So it's a multiplication, which is not commutative. So you have to be careful with minus signs. All right. Okay, so that's kind of a lightning review. I think I will actually link or add my video for Physics 1 students on cross products into this video feed. If you're comfortable with it, don't worry about it. But if otherwise, it's just there into this playlist. All right, the other. So that's perfectly fine. To be a little bit more efficient, though, it's handy to have kind of a computational set of results that, so you can work it out in components and then quickly do some cross products. It turns out that x hat cross y hat equals z hat. Let's check, does that make sense? Magnitude of A cross B, well, that's just 1 times 1. So the magnitude of this is 1, so that's okay. They're perpendicular. The answer is perpendicular to both the inputs. That makes sense. And then you mentally have to kind of picture it. If you align the palm of your hand towards the x-axis and curl your fingers to the y-axis, your thumb goes along the z-axis. So that's the right answer. Okay. And then you can make, if you kind of imagine this is, mentally, I imagine this is on a belt or a loop, and you kind of click it around so that, you know, maybe basically y moves to the left by 1, z moves to the left by 1, and x pops up on the other side, it's also true. So it's y hat cross z hat equals x hat, and z hat cross x hat equals y hat. Similarly, if I swap two of them, leaving the third fixed, you get a minus sign. So it's going to be y hat cross x hat equals minus z hat, z hat cross y hat equals minus x hat, and x hat cross z hat equals minus y hat. Okay, so hopefully those are familiar. You can kind of picture it. Take a second, maybe review the right-hand rule. Take a second. You should be able to very quickly verify that these are correct. Okay. That's fine. Those are useful things. And so then if you had small vectors with just a few components that aren't zero, or things that live in a plane, perhaps, I would do it this way. Just kind of write them out with basis vectors and just quickly cross product, take the cross products, and get your answer. Oh, I should also say all other products between basis vectors are zero. Okay, all others are zero. So if you have a vector with just a few components, it's probably just as easy to just write it out component-wise and do the multiplication. If you had a completely arbitrary vector, you can do it this way and just carefully grind through, multiply, you know, cross product, cross one vector into the other, work it out piece by piece by piece by piece. It's kind of tedious, and you have to watch your minus signs because we are in the habit of reordering things sometimes just automatically, but with cross products, it's not for free. You get minus signs. The other way, a final way to think about a cross product is in terms of a determinant, and this works in 3D. It doesn't work in other dimensions, but for us, it's okay. And that says that if I have a vector A, which is AX X hat plus AY Y hat plus AZ Z hat, and another vector B, which is BX X hat plus BY Y hat plus BZ Z hat. There's another way I can use a determinant to calculate A cross B. So here's the thing. You need a way to pair up pieces from A and pieces from B, and it has to pick out, first of all, it can't have anything, any diagonal terms or diagonal factors, and because it has to be anti-symmetric. And it also needs to just multiply the components. We don't want to do any further stretching. Well, that's exactly what a determinant does. It takes a little bit from here and a little bit from there, and it kind of comes up with an anti-symmetric combination and multiplies and adds up results. Well, that's exactly what we want. So it may look surprising at first, but if you think about what a determinant actually involves, it really is pulling out kind of the anti-symmetric information. Then it's not a surprise that the anti-symmetric cross product could be expressed in terms of the anti-symmetric properties of the determinant. And that's the basic idea. Okay, so the formula for doing this is to say this is the cross product of these two is the determinant of the following matrix. It's kind of weird. You put x hat, y hat, and z hat here, and then you put not the vector, but you put the components in the spots here. Ax, ay, az, bx, by, bz. And when you take the determinant, it's going to, so what's weird about this is it's a kind of a mixed character matrix. It's a matrix where some of the entries are vectors and some of them are just numbers, scalars. But we're really just using the determinant as a bookkeeping crutch for minus signs and anti-symmetry properties. So that's why, so then I guess that's why it's okay. It's weird in that sense. All right, and so you go through this and we learn that in general, A cross B equals, it's going to be AY BZ minus AZ BY times X hat minus AX BZ minus AZ BX Y hat plus AX BY minus BX AY Z hat. Okay, so I'm going to post that other video for my Physics 1 students in the playlist. So I'm writing these very quickly. Pause this video maybe and verify that you can get that from determinant properties, or you can work it out from the basis vectors themselves, but that's the result. Hopefully this should be familiar to you. If not, watch the other video. Okay, so after that quick aside, let's think about what this all means for magnetic forces. So the magnetic force law is of the following. It's on a point charge. Charge of the source, of the observer, times the velocity of the observer cross the magnetic field of the source. And so we know, well, first off, let's talk about units. This is a Newton, this is a Coulomb, this is going to have a meter per second for velocity, and this has units of magnetic field. So the units of a magnetic field are going to be newtons per Coulomb meter per second, which, so that's a kilogram meter per second divided by Coulomb meters per second. So that comes out to something crazy, a kilogram per Coulomb per second. I'll be honest, I work it out every time. I can't remember that. Okay, it's something bizarre. It turns out though, okay, so the name we give for this, because we don't want to, well, which is why I don't ever remember it. we define this combination to be 1 Tesla. Okay, 1 Tesla, named after the car. No, named after the person. 1 Tesla. Now, kind of like with coulombs, a coulomb is gigantic in terms of practical amounts of charge. 1 Tesla is gigantic in terms of magnetic fields. I think 1 Tesla is kind of like, you know, what an MRI machine generates. I mean, it's a huge magnetic field. We don't get anything near that under normal conditions. Oh, I want to rewrite that, sorry. I did want to rewrite this. One way you can write this, sorry, though, I meant to highlight this. Let's go back up here to the Newton language. You can write that, rearrange this fraction to be a Newton divided by a meter times a Coulomb divided by a second. I've just moved the second over, and I realize that that is nothing other than a Newton divided by an amp times a meter. That's going to be a better way to think of it anyway, because that's going to more closely mirror how we actually make magnetic fields. Something about currents. Okay, anyways, so 1 Tesla is defined, it's equal to all these. It's a huge amount of magnetic field. That's not what we have in more common. So we need a better unit, or oftentimes people use a better unit for more realistic situations. And people also use what's called a Gauss. And so 1 Gauss, people write as 1G. 1 Gauss is much smaller than a Tesla, because a Tesla is huge, and this is going to be more reasonable. This is going to be 10 to the negative 4 Tesla. Right? So it doesn't follow the usual metric set of conventions. This turns out, though, to be a more everyday size of magnetic field that people have. So when you have a problem, just read it carefully and you can do the unit conversion. It's just a factor of 10,000 between them. All right. Okay. All right, so now we've gone through units. Let's come back and think about what this means. Let's draw a simple case. Let's imagine that we are a bird flying over the board, over the plane, and coming into our eye is a magnetic field. So we're going to have magnetic field lines which go into your eye. And remember, into your eye is like an arrow tip coming into your eye. And we're going to take the magnetic field, which is in black, to be uniform, evenly spaced, so the strength is the same. They're all parallel and evenly spaced field lines. So the magnetic field is into your eye. And let's imagine we have a particle with charge Q, excuse me, moving to the right. Apologize. As I'm looking at the computer, it looks to the right to me, but I see that because I'm taller than the board, everything's got a drift to it. So I apologize. All right. So the particle has a velocity to the right. And for right now, let's assume that the particle has positive charge. Okay. So when I work this out, we're going to assume the charge is positive, the velocity is to the right, and the magnetic field is into your eye. So we're going to use the right hand rule to work this out. So what should you do? Step one, sit on your left hand. Okay, so you're going to use your right hand. It's so depressing to look up on an exam and see everybody writing with the right hand and using their left hand to do cross product stuff, because I just know they've got everything off by a minus sign. This is one place in life where lefties have an advantage because they can keep writing as they do their work. All right, so to work this out, we have right hand, V. So I put the palm of my hand, align it with the velocity, V, and I curl my fingers in the direction of the magnetic field. Oh, well, to do that, I have to twist my arm. So I have V, and I curl my fingers towards you, and my thumb now goes down. So if the charge is positive, so V cross B is going to go down, and if the charge is positive, then the force is going to be down. Okay, so that means that the force on this guy, I wish I had another color. Let me see if I got one now. My kids got a hold of my markers, and so I don't have lots of colors here. So I'll just have to draw it here. The force, so this was the velocity. This is the force. Interesting. Think about it. That's like tetherball, right? You're going this way, but the force is pulling you sideways. So you know what happens. You get yanked around, you start to turn. So now, let's say the particle's over here. It has a velocity going this way. Okay, let's work that out. So now I have to work out V cross B. So I do V cross B, curling kind of into your eye, V cross B, and I get a force, which is this way. So now over here, the force is this way, which is going to cause the particle to kind of yank around to be here. Like, interesting. So now, let's say we've got a velocity vector there, V cross B, I get a force going here. What you see is the following. Magnetic forces make circular motion. More generally, spiral motion. Spiral motions. That's weird. So when you put a particle in a magnetic field, it's like a tetherball, basically. The particle goes around and around and around, and it spirals. And you can see, because this was a cross product, that the force is always perpendicular to the velocity and the magnetic field. So when you have a magnetic field which points in the plane, and a particle moving in the plane, the force is always going to be perpendicular to both of them, and basically it's either going to, so all it can do is make it go in a curve one way, or so basically, in this case, a clockwise curve or a counterclockwise curve. That's all that could happen in this situation. So that's an important thing. And then the other thing to note is that we assumed that the particle had positive charge to get the minus signs. If the charge had been negative, there would have been one extra minus sign. And instead of kind of going around in a clockwise fashion, it would have gone in a counterclockwise fashion if the charges had been reversed. And in fact, when they look at particle collisions, one of the ways that they identify particles, and you say matter versus antimatter, is you will see these paths followed by two particles. Turns out the mass of the particle will determine the radius of the path. So you get a circle of a certain size that goes, say, clockwise. And then you'll see a circle of roughly the same size going counterclockwise. So these are two particles. their charge to mass ratio has to be the same in magnitude, but they're opposite to each other. And that's kind of a signature of antimatter. You're seeing two particles which are otherwise identical, except their charges are reversed. Okay. Okay, so that's what, qualitatively, that's what magnetic forces do. They make objects spiral. I say spiral because if the particle had initially had motion, say, let's say the particle had initially been moving kind of diagonally, so it was to the right and out of the board. Okay, well, when you do the cross product, the part of the velocity which was out of the board would give 0 to the cross product. So the only part that actually matters is the part in the board. So what would have happened in that case would be particle would be going this way, and it would have spiraled kind of into your eye. There would be no force in the z direction because the force has to be perpendicular to the magnetic field, which was in the z direction. Or sorry, there would have been no force into your eye because the magnetic force was already in your eye and the force is perpendicular to the magnetic field. So the only thing that force would have done is make it spiral. That's what happens in the northern lights. Okay, you have charged particles near the Earth's pole, which turns out is where the magnetic field is strongest, and particles get trapped, and as they fall to the Earth, they spiral down. It turns out, as they spiral down, they create their own electric and magnetic fields, and that gives rise to light. We'll talk about that later. Okay, so that's the magnetic force. Kind of go through my list here. This is what it does to charged particles, to point particles and currents too. It makes them follow through spiral kinds of motions. All right. Next time, I'm going to go through some properties of this new field, this magnetic field. Just these are going to be things that we observe, features we observe, and we'll do an example. Basically, we'll do this example. You'll have some sample questions like this. And what we'll do is be able to relate the frequency at which this particle goes around to properties of the charge and the mass, things like that. So, okay, so I'll see you guys in the next video.